This is lecture 5 of the electronics course, and we are continuing our discussion on semiconductor electronics. Last time we looked at some basics of diodes and transistors, and we saw how to properly bias a transistor. Today we are going to be looking at two of the main applications of transistors, and these are both amplifiers. So one is going to be the CE amplifier and the other is going to be a differential amplifier. So let's start with the discussion. So this is a CE amplifier. By CE we mean this is going to be in the common emitter mode. Last time we discussed that you can have transistorized circuits in the common base mode, common emitter mode, common collector mode. So this is specifically in the common emitter mode, so CE. The idea is we are going to construct an amplifier which takes in an AC input signal and outputs an amplified AC signal. So the circuit for this is as follows. First we have a transistor circuit which has been biased in the voltage divider bias, and this is something we saw last time. So let me just draw the circuit for a voltage divider bias. There's a plus VCC source, DC source. Then this is our voltage divider, R1, R2. And over here, I'm going to put the transistor. This is an NPN transistor. Collector resistance, emitter resistance. This is grounded. So this is the voltage divider bias transistor that we have seen last time. Nothing new in this. Now, I'm going to put over here one capacitor. Let's call it C1. And this over here is Vs, which is the input source. And remember, this is AC because it's an AC signal that we want to amplify. I'm going to take the out, so let's call this base, collector, emitter. At the collector, I'm going to take my output. I'm going to put one more capacitor over here, call it C2. And here I'm going to take my output. So across this and the ground. So I'll put one load resistance over here. And I'm going to put across the emitter, I'm going to connect what is called a bypass capacitor. So I'll call it the emitter bypass capacitor. Let me tell you why I put these capacitors. See, I want to amplify an AC signal. I want to see the effect of an AC voltage on this circuit. So I don't want any DC component. Now, as we have seen before, a capacitor allows AC current to pass through. And if the frequency is high enough, then the impedance is very small. So we are going to assume in this that we are using a high frequency input. So the capacitor, as far as AC is concerned, the capacitor is almost like a short. So the capacitor will allow AC signals to go through, but it will block all DC signals. So it will make sure that in the input that we are giving and the output that we are getting out, there is no unwanted DC component. What we are getting is pure AC. That's why we put these C1 and C2 capacitors. Why do we put this? What is the point of this emitter bypass capacitor CE? It makes sure that for the AC signal, the emitter is as good as the ground. So as you can see, the AC signal will not pass through the resistor, it will only pass through the capacitor because the capacitor offers it hardly any resistance. So as far as the AC signal is concerned, emitter and ground are at the same potential. Now, as you can see, this circuit is quite complicated. Question is, how should we analyze it? So in this, we are going to take the help of our old friend, the superposition principle. Which says that you can analyze your sources one at a time. You don't need to deal with everything together. So what we are going to do is, first we are going to do what is called the DC analysis. and then we are going to do what is called the AC analysis. So let's start with this. The superposition theorem says that if you are considering one source at a time, you set all other sources to be 0. So since we are doing DC analysis, we will set our AC sources to be 0. So basically there is no AC in the circuit. Vs has gone to 0, and wherever there is a capacitor, since DC cannot pass through it, it is as good as that connection not being there. It's like an open circuit over there. So the DC equivalent circuit looks something like this. R1, R2, RC, RB. Oh, sorry. Forgot the main thing. Base, collector, emitter. So this is our DC equivalent circuit, and this is exactly the voltage divider bias transistor that we saw last time. So what can you do with this? First of all, you can find out what is the resistance at the what is the potential at the base. So can I write over here? Yeah. Potential at the base. So over here, as you can see, this part is a voltage divider that we have been seeing since our first lecture. So the potential at the base is just VCC R2 divided by R1 plus R2. Yeah. Now we know the potential at the base, so we can find out what is the potential at the emitter. Potential at the emitter is just potential at the base minus VBE. And VBE, we know from diode characteristics, it's going to have some fixed value. It's going to be around 0.6, 0.7 volts for a silicon diode. It's going to be around 0.3 volts for a germanium diode. So VBE is practically constant. So since we now know VB and VBE, we know VE. If you know the potential at the emitter, then you know the current flowing through the emitter, because this current IE is just VE minus ground divided by RE. So of course I didn't specify it, but it's since this circuit is something we have constructed, we know what the values of the resistances and the capacitances are. So we know R1, R2, RC, RE. These are all known quantities. We just want to find out what are the currents, and using those we want to eventually find out what is the voltage gain. So if you put some input signal, then how much, by what factor will it increase to give you the output. That is our ultimate aim in doing this entire analysis. So we have found out IE, and we know that IC is roughly equal to IE. So therefore we know IC also now. And finally we know that from the load line equation we can write VCC is ICRC plus VCE plus IERE. That is this. This is the DC load line equation. VCC we know, IC we know now, RC we know, IE we know, RE we know. So therefore now we also know what is VCE. So this was the DC analysis of this circuit. Now we want to see what happens when we do an AC analysis. Before we start doing this AC analysis, let's just look at the input characteristics. Well, actually, not exactly the input characteristics. This is VBE versus IE. So from the diode characteristics, we know that the plot of this potential versus current over here, the graph looks as follows. And let's say our Q point is somewhere over here. This is the Q point that we have chosen. Q point is the operating point of our circuit. So along VBE is the input that we are getting, along IE is the output that we are interested in. So let's see what happens if we give a large input signal at VBE. Since we are interested in giving an AC, suppose I give a large AC signal like this, then what will the output look like? Then pulling it on this side, you see that the output will look something like this. In other words, if you put a large input signal, there is going to be a distortion of the output. You can see that the two lobes are definitely not equal. Even though we started out with a symmetric input where the positive cycle and the negative cycle is the same, in the output that is not so. So this results in distortion if the signal is large. And this is going to be a problem. So we always make sure that whenever we are doing this kind of analysis, we are doing it in the context of a small signal. So we are using small AC inputs. Such that the distortion is minimized. So with this assumption now, let us try to draw what the AC equivalent circuit will look like. Let's go to the next page because I want to put both circuits side by side. So the full circuit, let me just draw it again for you. Emitter resistance, collector resistance, R1, R2. These are our two DC blocking capacitors. This is our emitter bypass capacitor. We have a load resistance. Now let's try and redraw this for an AC circuit. So the AC equivalent circuit for this looks as follows. Remember now, because we're dealing with AC circuits, capacitors I can replace with shorts because the AC signal is going to pass through the capacitor without any problems. All DC sources have to be set to 0. So VCC is essentially gone to 0. VCC has become ground. So let's start from the left. Vs. There is no C1. I have shorted it. Now from this point, R2 goes to the ground. Okay, R2 has gone to the ground. From this point going up, R1 goes to VCC, but I said VCC has also become ground. So basically from here, VCC R1 has also gone to ground. Then going further right, I have my transistor. From the emitter, see there is RE and then in parallel with that there is CE. But all the current is going to pass through CE because it hardly offers any impedance. So RE then is as good as not there. It's like having RE parallel with a zero resistor, so overall resistance becomes zero. So this also goes to ground directly. There is no RE. From the collector, RC goes to VCC, but RC has also, but VCC has also, again, it has gone to ground. So this also I will take it to the ground. And then from here, there is no C2. And directly I will take V out over here across the load resistance. So all of these points are at the same potential, which is the ground potential. So this is our AC equivalent circuit. Make sure you understand how this circuit came about. If you need, go back and look at it again. This is the AC equivalent circuit that you get by setting VCC to 0 or ground and by replacing all of your capacitors with shorts. Let's simplify this a little bit. Equivalently, I can draw, I will just call this one over here R1 parallel R2, then the transistor, and this, which is RC parallel RL, is called small rc, or it is called the AC collector resistance. So this is our simplified version of the AC equivalent circuit. I just want to specify one thing, that this is notation. So usually when one is doing DC analysis of these kind of circuits, one uses capital letters for all the currents and resistors. When one is doing AC analysis, one uses small letters. So this AC collector resistance RC parallel RL is denoted by small rc. Similarly, as we will just see very shortly, all the currents, the AC currents that we see, those also we will represent in terms of small letters.